All right, the normal distribution, you may have heard of it before. You may have heard of a bell curve before. If not, I'll tell you what it looks like. Normal and skewed distributions are what we're talking about right now. A continuous probability distribution is represented by a curve. This is not actually intersecting the x-axis. Things that are outside of the arrows would be outliers. Now, these are types of continuous distributions. This is the normal curve. So what would be here in the middle would be your mean. Okay, that's where your average is, or the mean. And what's interesting about the normal curve is the mean, median, and mode are actually the same. So I'm not going to split this up until we get to the empirical rule, and I'll discuss this some more. But notice that it's evenly distributed to the left and right of the mean. That's a normal curve. So if something approaches this curve, we call it normal. If something has the most of its data clumped over here, this is the part that's off and not really following the other part. This is called positively skewed because it's flattening out in the positive direction. Okay, this is called negatively skewed. It's flattening out to the left. Okay, which is another way to call it skewed right, pointing that way, skewed left, pointing that way. Okay, so the data is not evenly distributed. So we'll do an example. Determine whether the data below appear to be positively skewed, negatively skewed, or normally distributed. This is the list of the data. It's already, a frequency table has already been made for the data. All the numbers were repeated some amount of times. One way to just look at the table and tell if it's skewed normally or not is to see if there's a larger amount in the middle, and then if it's ordered from smallest to largest, and if these are kind of smaller than the middle, and the middle's a little like bigger than maybe even the sum of them almost, you know, that's kind of seems like this is going to be normally distributed. Another way is just kind of connect these and look and see if it looks kind of like the bell curve, and this does. So because this histogram is roughly symmetrical, the data appear to be normally distributed. Okay, we're going to make our own histogram here. We're going to determine whether the data appear to be positively skewed, negatively skewed, bless you, or normally distributed. Make a histogram of the data. All right, let's start with 22. So I'm just going to put some kind of mark by 22 to count them up. I have 1, 2, 3, 4 22s. So I'll make a bar up to 4. And then I'll go for the next numbers, 24. 1, 2, 3, 4, 5 24s. So I made a bar for that. You don't have to shade them in if you feel like it. You can, but whatever. For 25, and I'm lucky I got a bunch of colors. We got 25 once, twice, 3, 4. Did I miss any? 4 of them? And then 27s, there are 2, 3, and then 29. How many 29s? Let's see, there's 2 of them. All right, so this is kind of bunched up on one side, isn't it? So I look at the way that's trending, it looks like it's positively skewed. But another way to say that, and I just messed up that word, skewed. Positively skewed, or you can call it skewed right. Right? Another example of shoe size. We plot the different number of people with a certain shoe size. There's only one with a size 4, some little peanut. 5, there are 2 people. See all these little feet. 4 people with size 6. And then the people with the size 7, things feet are getting bigger. 8 of them. 5 with a size 8. Oh, 1 with a size 9 and 2 with a 10. So if you kind of just connect those bars, I know it's a little off, but this looks pretty normally distributed. Now, it's not ever going to, when you have that small of a sample size, it's never going to really be truly perfectly normal. Got the idea? Anybody with a shoe size, well, I don't think there are any smaller than 4. Well, I guess there are. Then you'd have to go to the kiddie shoes, right? And I'm thinking this data seems more like women, don't you? Well, feet have been getting bigger. Do you know that? Over years, feet are getting bigger. Yeah, their average size is a little larger than it used to be. Okay, we've got this housing situation on this next page. I don't think you have a whole lot of problems, but after this, this one I think I'm gonna let you practice the rest for assignment. Okay, let's make another bar graph. How many houses were sold or less than 100,000? Well, for this group, it was 0. But at least you can see the categories down here. From 101,000 to 120,000, or 100,000 to 120,000, there's 1. Okay, and then next category's got 3 homes sold. Next category, 7. And then next category is 8. And the last category, oh no, there's one more, 6. And then the majority of the people over 200,000, 12. Okay, so this is definitely skewed. It's negatively skewed. Or skewed left. Okay, so I'll leave those others for you to practice, and what we're going to go to now is the empirical rule. Okay, there is a special rule about the normal distribution. The mean is always right smack in the middle. That would be no standard deviations. That is where the mean is. If you like the color, you might want to have a highlighter for a couple of things we're going to look at. The normal distributions have the following properties. The graph is maximized at the mean. That's where the high point would be, where the mean is. That means most of the data is clustered about the mean. And there's a specific way it is clustered about the mean. And the mean, median, and mode are about the same right here. Okay, so that for a normal distribution, mean, median, mode are basically the same. About 68% of the values are within 1 standard deviation of the mean. Now, what is that? Well, the standard deviations, this standard for standard deviation. Okay, so 68% lie within 1 standard deviation of the mean, which would be all of this. From here to here is 68% of your data. Now, if you wanted to think about it, we want to know if we're above or below the mean for a lot of different situations. We want to look at, say, how many people are expected to be a standard deviation below the mean, or maybe how many people are expected to be a standard deviation above the mean. So if that's 68%, and this is symmetric, then what percent's here? Half of 68, 34% there, 34% here. All right, and then you have 95% within 2 standard deviations of the mean. So that's going to tell me something about this. So I'm going to figure out what those sections, what percent those sections are, because that can be very useful. So what's the difference between 95 and 68? So I did 95 minus 68%. What do we got? That's 27, right? Now that's shared between the 2 yellow pieces. So 27 divided by 2 would give me 13.5% here, 13.5% in this section. Which means to the 2 standard deviations to the right of the mean would be 47.5% of the data, right? And 2 standard deviations to the left of the mean would be 47.5% of the data. But most of the data lies within 3 standard deviations of the mean. So you got this little bit down here where these are actually even where sometimes outliers lie. If they're really big outliers, then they're going to be outside of these 3 standard deviations. But check it out. 99.7% of the values are within these 3 standard deviations of the mean. Now, you already used up 95%, so what percent more do we have to look at here? Okay, that's 4.7%. We need to break it apart to get the pink area, which would be that divided by 2, which is 2.35% on each end. Okay, so that's 2.35%, and this is 2.35%. Now let's think about the last thing that we haven't yet, which would be what's beyond 3 standard deviations. Okay, well, what do we got left? 99.7% is within 3 standard deviations of a true normal curve. Then what's outside? 0.3%, and that gets divided by 2 to get my green areas, my tails, which is only 0.15% to the right or the left of 3 standard deviations. 0.15%. Everything we wrote was as a percent, not a decimal. All right, now we're going to talk about this and answer some questions. So, the heights of players in a basketball league are normally distributed with a mean of 6'1" and a standard deviation of 2 inches. This, it says, well, what's the probability that a player selected at random will be shorter than 5'9"? Okay, so what you would do if you're doing this problem is you would draw a normal curve, putting 6'1" in the middle, which is the mean. You would then add 2 inches and put 6'3", standard deviation to the right. Subtract 2 inches, put 5'11" as a standard deviation to the left. How much of the data is within here? 68%. That's where we're going to use the empirical rule, which means this part would be 34, this part would be 34. So you just got to try to remember those. By the way, you're going to get a picture of the empirical rule on a sheet. Okay, you'll have it. You have to know how to use it or make your own. Okay, so here's our question. What's the probability that a player selected at random will be shorter than 5'9"? So here's 5'9". The value of 5'9" inches is 2 standard deviations away from the mean. So approximately 2.5% of the players will be, and how they get that. So I want to explain how they're getting that. Within, from here to here, 2 standard deviations to the left and the right is 95% of the data, right? 2 within 2. Okay, so if we have 95%, what they did was do 100% minus 95%, which gave them 5% left. But that would be whatever's to the right of that standard deviations and whatever's to the left, and that's cut. You have to divide that by 2. So that's where they're getting 2.5% of the players would be shorter than 5'9". Okay. Everything we wrote on we have to think about what pieces of this puzzle we have to use to get the answer. If there are 240 players in the league, about how many players are taller than 6'3"? Well, what's 6'3" on here? All right, 6'3" is only one standard deviation to the right of the mean. But what would we be including? So you'd actually be including all the way up to here, which is one standard deviation, but you got everything over there as well, right? Here's where the mean is, okay? So this is percent. Get what I'm saying? Half of the people that are on the left of the mean. And then how much is within one standard deviation right here? Now you know why I broke that chunk up, which is 34%. So we need 50% plus 34% to know how many people are not included in what we're talking about. Okay, so we're trying to find out what percent is over here. Okay, so above 6'3". So if we do 100% minus 50 minus 34, or minus 80%, we get 16% left. With me? Like how I got the 16%? I had to take the 50%. I had to put a 34 on it, add that to it, and now I've got my 16% of the players would be taller than 6'3". Now, the last step here is to take 240 to find out how many times 0.16, and that's going to give you the 38. Okay, so I want to explain to you how we're getting these answers. Got? The ones that I put on the empirical rule, yes, you can do that because I figured them all out with you, but it's not going to be written on your. Okay, you're not going to have all of what I wrote on the sheet, so I want to show you how to figure it out also without looking at all those percents that I wrote down for you. Okay, so I'm trying to make you figure it out by remembering 68 within 1, 95 within 2, okay, and 99.7 within 3. That's what you're going to be given. I hope that makes sense why I might have done it this way. So it's not like you couldn't have done it differently, though, if based on what I've told you from the very get-go. Okay. That's egg production, because we want to learn practice drawing these and understanding how we're getting these things. All right, so egg production, the number of eggs laid per year by a particular breed of chicken is normally distributed with a mean of 225 and a standard deviation of 110. Of 10. Excuse me, I don't know what just happened to me. All right, about what percent of the chickens will lay between 215 and 235 eggs per year? All right, so let's make, I think you have a little bitty room over here, maybe to draw a little curve. I'm going to do it up here. Okay, so within 1, I don't know why I made that so close to my words when I don't have to. I'm just moving it. You guys do what you want. And I'm not making these all beautiful. But here's the point. You got a mean of 225. And you don't have to have a picture to figure some of this out, but I just think a lot of times that helps. One standard deviation to the right and left. What would be those labels? It says a standard deviation of 10 eggs. So it'd be 235, one standard deviation to the right. And then after that, standard deviations to the right would be 245. To go to the left, it'd be 215. And then one more down would be 205. So let's see what we needed. It says, what percent of the chickens will lay between 215 and 235? Well, that's between 2 standard deviations of the mean. Uh-oh. I didn't go all the way to 245. So you see what I need to do? I need to stop at 235. I can't assume it's even on either side of the mean. So 215 215 to 235 is at, what did I do? Did I label that thing wrong? This is 215, isn't it? Oh my gosh, I need to start over. All right, here we go. I put out 3 on this side for some stupid reason. This is 215. So now I went too far to the left. Gosh, I did this all right this morning. I don't know what happened. Maybe my lunch made me have brain issues. All right, 215 to 235, guys. My bad. I started making too many marks. That is between 1 on either side, so it was symmetric. Wow, we'll get to one that's not, but here we go. That's where within 1 standard deviation, it's 68% of the eggs. I made it too hard. Okay, that's 1 standard deviation on plus or minus 1 standard deviation. Okay, in a flock of 400 chickens, about how many would you expect to lay more than 245 eggs per year? All right, now you might already be able to do that off of what I told you earlier, but let me show you again how to figure out without knowing all that. If you have 50% over here, okay, this is 34%, and then this was 13.5. We're trying to know about how many are above 245. So that's going to be everything over here. What percent that is. So if I do 50 plus 34 plus 13.5, add all that up, what's that, 84, 94, 97.5? Did I add that up right? Yes. Then you could do 100 minus 97.5 and find out what percent that is. It's 2.5%, right? Now, 2.5% of 400 would be our next calculation. So we have to change 2.5% to a decimal, which is 0.025. Multiply that times 400 chickens. How many chickens should be laying eggs that are over 245 in 1 year? 10 of them? Okay. 10 chickens. Okay. Don't care how you choose to do it. By the way, if you just did 34 plus 13.5, you could subtract that from 50. You'd get to 2.5% that way as well. It's not the only way to do it. All right. Manufacturing. The diameter of bolts produced by a manufacturing plant is normally distributed with a mean of 18 millimeters and a standard deviation of 0.2. What percent of bolts coming off the assembly line have a diameter greater than 18.4 millimeters? Well, I'm just going to go ahead and look at what this is. 18 in the middle. 1 standard deviation, 18.2. 2 standard deviations, 18.4. Now it said, what percent of the bolts have a diameter greater than 8.4? That again is to the right of 2 standard deviations, which we just figured out in the last problem, wasn't it? Okay, this part would be 2.5%. Because 95% is within 2 standard deviations of the mean. 100 minus 95 is 5%. You split that in 2 to get the 2.5%. Okay, so next, if you want to note this, 0.4 is 2 standard deviations from the mean. All right. What percent have a diameter between 17.8 and 18.2? Well, let's figure out where 17.8 would go. If you it'd be right here. 1 standard deviation to the left of the mean, because you do 18 minus 0.2. That's how you get that one. What percent have a diameter between? That's within 1 standard deviation on either side, so it'd be 68%. Okay, those guys are 1 standard deviation from the mean. Yes, Scott. Oh, 2.5%. Forgot I didn't write it down anywhere but over there. Temperature. The daily surface temperature of a lake at a resort is a mean of 82 degrees and a standard deviation of 4.2 degrees. If you prefer to swim when the temperature is at least 77.8 degrees, about what percent of the days does the temperature meet your preference? All right, might as well do a little sketch. You don't have a lot of room. I see you have a little bit on the far right. Got our mean of 82, standard deviation of 4.2. If you went and did 82 minus 4.2 and 82 plus 4.2, that'll help you get this labeled one standard deviation away, would be 86.2 on the right. I don't think I even need that. That's above what he wants. We really want to look at what's below. What's 82 minus 4.2%? Or degrees. I have 77.8. Okay, and he likes to swim when it's at least 77.8. So we want everything, all of the days that are above, what percent of the days are above this temperature. So this is one standard deviation of the mean to the left would be 34%, and how much is over here? 50%. So 84% of the days is how many of the days or what percent of the days it will be good for him. But it said if you prefer to swim and it's at least that, what percent? Oh, that's all they want. They didn't have any number of days or anything, so 84%. Okay, so what I have is for some practice for you on 6B. That I can help you with if you need it, but you want to give them some of them a shot. And that's the last lesson we have. That's new stuff. The rest is going to be review, etc.